broad skill set applicable across contexts and domains. So it is not that it is only for mathematics. It can be incorporated in, and it has been incorporated in many subjects. And there are a lot of there's a lot of research on this. So I will not make it a research-oriented session, this one. But what does Wikipedia say about the definition of CT? It says that it is a set of problem-solving methods that involve expressing problems and their solutions in a way that a computer can also execute. But we need to understand computer probably in a more abstract sense, and not confuse it only with computing technology and programming. So a unified definition of CT is still elusive, and definitions range from being able to think like a computer scientist to problem solving, where problems are broken down in a way so that it can be solved by a computer. So this is broadly what. And of course, when you talk of CD, you can't not mention Samuel Papert, who he had worked and he brought this term way back in the 1960s and 70s. And he vividly talked about children using computers as instruments for learning, and he truly concretized this term. And constructionism is the school of thought which emerged from this. And later on in 2006, Jeanette Wing published a paper, and in that it is a short paper, but it kind of it started a lot of debate and discussion on CT, in which he said many things, but one of the key phrases she said was computational thinking is a fundamental skill for everyone, not just for computer scientists. So she said, like to the three R's, reading, writing, and arithmetic, we need to add computational thinking to every child's analytical ability. So this led to a lot of uh, debate and thinking and discussion on this term. So there are many frameworks. People have talked about computational thinking skills, computational thinking dispositions. What are the ways of thinking that children should inculcate, students should inculcate to engage in computational thinking? But one of the most common frameworks is where we talk of CT concepts as four stages. Decomposition, where you decompose a problem into simpler uh, subproblems. Then from data and from solutions or problems, we try to find patterns and we try to generalize those patterns, engage in abstraction, and finally, we also want, if we want to get a machine to solve the problem, then can we make it amenable to solution by computer? Then there are researchers such as David Winthrop and his group, who have listed out computational thinking skills. And many of these, obviously, we all agree are also mathematical thinking skills. So the ability to deal with open-ended problems. Uh, the word struggling came up, right, earlier also in the session. So to struggle with the problem. So persistence and confidence in dealing with complexity. Representing ideas in computationally meaningful ways. Creating abstractions. So this is a list. So I don't want to just read out a list, but we'll try to engage in some problems. Uh, The PISA 2021 framework has also acknowledged, they talk about the synergistic but reciprocal relationship between mathematical and computational thinking, saying that they are similar, so there are overlaps, but there are also differences between them. And NEP, of course, you have already seen this, said that right from the foundational stage, through a variety of innovative methods and regular use of puzzles and games, uh, we need to make mathematical thinking more enjoyable and engaging. So it's not easy to put things in bins and say this is CT and this is MT. But if we talk of overlap, probably problem solving, dealing with recursion, modeling, simulation, probably this will come under as an overlap. And CT focuses probably more on procedures and understanding procedures and how to make them solvable by a computer or a machine. And coding will be also involved, but that is not the only part of CT. In mathematics, perhaps it is more about proof, more about justifying argumentation, more about justifying solutions. Again, this is a very rudimentary, this is not really a research-oriented classification. So there are mathematical thinking and CT skills are mutually supportive and they are distinct. But the point is that what does a teacher do and how do we bring this about? How do we decide on tasks which enable children to engage with both kinds of thinking? So, technology, of course, you've already seen a wonderful session on GeoGebra. You've seen a wonderful session on computer algebra by Amber. And so you've seen some of the tremendous possibilities of these tools. And how can these tools, if used appropriately, can they play a significant role in mediating these two, CT and MT? So, of course, this probably should have been the last slide, but the the kind of tasks that you can do in computational thinking in mathematics probably can be classified into unplugged, what the terms are used. So unplugged is dealing with puzzles, so Sudoku, Kakuro, cryptarithms, games if you explore games and winning strategies. So simple games like tic-tac-toe or the game of name Tower of Hanoi. All these you can treat them as unplugged activities, and more if the problems are amenable to exploration via digital tools, we can of course call them plugged. But what could be some curricular themes or areas? So simple counting problems, I think, should be encouraged in the classroom. So starting with Sudoku, number of solutions that a Sudoku grid can have, or counting the number of squares and rectangles on a chessboard. These are all simple counting problems, but they lead to insight. Games and their winning strategies. This can be another area which can be incorporated in the school curriculum. Iteration and recursion. So here is where fractals. So now Amba did an excellent session on where we saw Julia sets and Mandelbrot sets. But if you have to make young children explore with fractals, what can we do? What kind of simple hands-on exercises that they can do? Perhaps we can look at that. Data handling is an area which I think representing data meaningfully, this is an area definitely which needs exploration and where CT can be incorporated. Geometrical constructions using dynamic software, devising methods for constructing different kinds of figures with different constraints. Mathematical modeling, again, this is just a list, and probability simulating games or other phenomena. So this is something, these are some of the areas and there could be more, but these are some of the initial things I would like to suggest. So again, I'm not an expert in computational thinking, I'm just learning. And so maybe just as a warm up, because everybody is quite tired, we just engage with a simple, interesting problem. I would request everyone to take out your notepads, and I would like to see some drawings if possible. So we have an act we have a two pan balance and 9 coins of identical appearance, of which we know that the one weighs less than the others. So it is a faulty coin. So 9 coins look exactly the same, but one is counterfeit or it's faulty. And what is the least number of weighings required to identify that faulty coin? But no weights are available. So basically, you can weigh the coins against each other, but you can't do anything more. So you just have that two pan balance and you have these 9 coins which look identical. So can you suggest any ways you think that? So again, while I do this session, I would also like to, these were all tried out with school students and also with my first year students who don't come with who many of them who left mathematics after class 10. So you have to bring in problems which are not based on calculus and other things. So how did they also think about it? I can share a little bit of that. But first, if you could suggest, anyone can speak. And so there are 9 coins which look exactly the same. We have to weigh, obviously you weigh some against each other, but what is the minimum number of weighings which is needed to identify the faulty coin? So I have got one answer from Fozia, which says, she says two, right? Two. Everyone says two? So you're saying that minimum. Certainly will be. Yeah. It's the minimum number of weighings which would lead to the identifying that faulty. Anyone from that side? What any thought process here? three. I've got three, but I've also got two. Now, which should it be? So if three, Geeta, could you share how would you like to go about it? I would take four and four and weigh it in a pan. If they're equal, then the coin left out is the counter. Correct. And if one is higher and the other is lower, then the count of which coin is in the lower. So now I have four. I've reduced the problem from nine to four. So again, I pick two and two. Whichever is lower, that has the thing. Then I put one and one, whichever is lower. Everyone agrees with this? Sorry? 9 coins. So 333. Yeah. Okay. So would you like to say three? Why did you say two? Okay. Or not. And then you will find out. Okay. So the solution is that your solution also? No, mine was slightly different. Okay. Three. The one is the same as Gita? Okay. So this solution says two wings required. So you one way is to split them into four, four, and one. But then you will need three wings. But if you do three groups of three coins, दो sets को आपने balance पे रखा. If they balance, then the third set has the faulty coin, right? Once you've identified which three has the faulty coin, you take that set, जो भी है, अगर इन दोनों में से कोई कम ज्यादा है, तो जो कम है उसमें faulty है. The first weighing W1 helps you identify which is the set, which three has the faulty coin. Once you identify three, then you just need one more weighing. क्योंकि तीन में से कोई भी दो ले लीजिए. You weigh them. If they are equal, then the third one is the faulty one, and if they are not equal, then the lighter one is. So it's a very easy solution. But there's nothing wrong or right. But the minimum number of weighings is two. So what happened when, interestingly, so later on, when I gave this to my students, there was a discussion and all. I asked them, how would you represent this solution? Can someone say, would you like to say it in step language? Or what are other ways of representing the solution जो अभी हमने discuss किया? How would you suggest? So here, in one way is that you can ask students that let N represent the number of coins and Tn represent the minimum number of weighings required. So what will happen for 2 up to 9, 2, 3, 4? So sometimes students get a little confused. So decomposition means you take simpler case. 9 में अगर नहीं सोच पा रहे हैं, so let's go back. What will happen with 2, 3, 4, 5, and then they'll see a pattern and probably they will start. Okay, can you tell me if there are 2 coins, then how many weighings are required? One. If there are three, then also one. If there are four, with four it goes to two because दोनों side से दो रखेंगे. Then whichever is lighter, then you have to do one more wing. For five, so two goes up to 9, right? So five also will 2, 3, or 6 also 2. So right from 4 coins to 9 coins, the minimum number of wings will be 2. But when do we need 3 then? What about 10? For 10 coins, will we need 3 wings? Why? Can anyone share? For 10 coins, what we should do? Okay. But can we extend the 3 3 wala case to 10 also? If we have 3 3 3 and 1. If the two that you are weighing, one is lesser than you have already identified the 3 coins which will have the faulty. But if you take equal, then there are 4 others. And we've already said that for 4 we need 2 weights. So it is 3. So 10 से शुरू करके we need 3 wings. Up to what? Up to how many coins do we need 3 wings? कितने coins तक 3 wings में हम पता कर सकते हैं कि कौन सा coin faulty है? Yes, sir. 15. अच्छा. Okay, 15 में कैसे होगा sir? If you can explain. You making 3 sets of 5 coins? 16 में भी 3 चाहिए? 3 से हो जाएगा? Is it optimal to half or it is optimal to take thirds? That's in the first step. So this is what students also discussed. And of course, we went to what happens as we are discussing now. What happens if the number of coins is increased beyond 9? So obviously, like you did, one solution strategy was divided into half if n is even, and if n is odd, then take 2 equal sets and leaving out 1 coin. The other group argued that no, it will be more optimal if you take n by 3, which we have already agreed upon. Okay, so before I move to the next slide, so have we agreed on what is the maximum number of coins for which 3 weighings will suffice? So, so we agreed that for 10 we will need 3 weighings. Okay? For 11, of course. And someone says 15. 15 said 3 weighings mein ho jayega? For 15 coins. What about 16? Huh? Why? Absolutely. This is the correct. So when there are 27 coins, you can make 3 sets of 9 coins each. The first weighing will tell us which 9 coins has the faulty coin. Do you agree? But we already have shown that for 9 coins, the minimum number of weighings is 2. So for 27, it should be 3. So some kind of recursion in our thinking can take place. And if you try to sort of generalize this, so okay. So when students were asked, so then some suggested, ma'am, we can draw pictures and kind of made a sort of what we can call it a tree or a decision tree or something. So this is a handwritten, so it's just a snapshot. So numbering the coins is 1, 2, 3, 4, 5, 6, 7, 8, 9. So here they are saying 3 possibilities. 1, 2, 3 is equal to 4, 5, 6, then the faulty one will be 7, 8, 9. And if the faulty is in 7, 8, 9, pick any two from there, weigh them against each other. And if they're equal, then 9 is the faulty coin. If 7 is less than 8, then 8. So this strategy, it shows all the possible cases without saying much in language and drawing a picture. So sometimes drawing a picture can be very insightful. And if the younger, my experience has been the younger children you approach, they tend to draw pictures and explain more than trying to use some method or formula. Sorry. So, so of course, then students started creating their own questions for exploration. And that was if there is a pile of 15 coins. Okay, so we already discussed 15 coins. For some reason, 15 seemed interesting to them. Now somebody said that okay, what if there are 9 identical looking coins and there are 2 faulty and 2 are defective and it is not both are heavier or both are light. By the way, what we just discussed, if the faulty coin was heavier than the normal coin, the same argument will apply because by symmetry we can have it. So if it is known which is heavier or whether the faulty coin is heavier or lighter, then of course we can get solutions easily. So they created pictorial solutions. Now this is just a snapshot. I have taken permission from the student to share. So this group, now you said 15. 15 में हमने क्या सोचा था हम पांच 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 के ग्रुप्स बनाएंगे दो ग्रुप्स को मेजर करेंगे if they are equal in the third group and 5 के लिए what is the minimum weight 2 so 5 में भी हम दो दो रखेंगे and then we will decide this group has done something completely different. It took me some while to understand if you look closely at the picture So they are saying let's color code and make groups of five red, five blue, and five yellow. Now, if you look at the middle part, the first weighing is you weigh the red versus the blue. If they're equal, that means the yellow has the obviously has the 40. But in the second weighing, they did something with mixing. And in fact, they did not have experience of coin weighing problems. But this is also a strategy which is used. Okay, so they took 11, 12, 13, and they interchanged. They maintained 4 and 5 on this side, the red color. They put 11, 12, 13 here. And 1, 2, 3, we have to see if there's any flaw in their argument. And 14, 15 को इस तरफ रख दिया. And they're saying that these two will not be equal. Why? Obviously, because one of the coins, the yellow coins, is faulty. So either one side will be heavier or one side will be light. So if it is heavier, then which three will be defective, and then they from that they further segregate. So it is not a solution which we thought of. It's a little different from that. And the same kind of argument will work if we mix if the red group turns out to be lighter than the blue group and so on. So here we can see that when students are engaging with this problem, they're thinking in different ways, different kinds of solutions. And what was interesting and heartening to see is that many of the students who got involved in this problem, they claimed that they had a lot of fear of mathematics and all. So they said, "ये तो maths नहीं है. We're solving a puzzle. We're just thinking about this problem." So they engaged with it, and and here, of course, they had to identify which is the defective point. So in some case, here the last one case, this is an impossible case because we know that if you mix the yellow with the red, then both sides cannot be turn out to be equal. So either one of the other two cases will be possible. Then generalizing this, so we know that for 10 to 20, so for 2 and 3, it's only 1. For 5 to for 4 it is 2. For 5 to 8 it remains 2. But for 9 also we need. For 9 is the highest number of coins for which we can manage with 2 ways. 10 to 27 it is 3. So it is something to do with powers of 3. So obviously if there are 81 coins, then you can do with 4 and so on. So we can generalize and say that if the number of coins lies between 3 raised to the n minus 1 and 3 raised to the n, then the minimum number of weighings will be n. So this was a kind of, they did not go further. They did go a little further, but that I will not be able to discuss right now. But there is a much more exciting case is when there is a faulty coin, but we don't know whether it is heavier or not. So that's a very big challenge. अगर हमें पता ही नहीं है कि कौन जो है faulty coin है वो heavy है या light है in comparison to the normal coin, then it's a challenge. So how how can you find victors? Of course, this was solved. I mean, this was thought about, but and you have to identify which coin it is. Identify the faulty coin and whether it is heavier or lighter than the regular coin. So this, of course, has a handwritten solution. Of course, but this is more complex. Again, here you do that some kind of mixing. So you have, but you do start with dividing the coins into 3 sets. So you number them 1, 2, 3, 4, 5, 6, 7, 8, and let's say 9, 10, 11, 12 is the third set. And from that, so if E means if these two are equal, then what happens? These are all good coins because they are equal. So we take some 3 from the faulty set, proposed faulty set, and compare them with 3 of the good coins. And then we try to find. So for example, suppose I know that 9, 10, 11, 12 में faulty coin है. So I take 9, 10, 11 and I take let's say any of these 1, 2, 3. If they are equal, then what does it mean? The faulty coin has to be 12. But is it heavier or lighter? So it has to be compared with the good coin to see whether it's heavier or lighter. So they are more complex cases, but now we can see, we can identify the red triangles indicate that we've been able to identify whether the coin is heavier or lighter. So I won't just keep doing this because then we'll spend the entire workshop doing this. But These are well worth, these kind of problems are worth investigating, and they engage, they are what we can identify as low threshold and high ceiling. That means anyone can try, everyone can try the problem. And probably if someone wants to take more complex situations, they can do so. Okay, so we've already had a very nice session on fractals, but so maybe I'll just this is again a topic which I strongly feel should be incorporated in the school curriculum. And so all around in nature, we do see examples of self-similarity. And whether you take the cross-section of a cauliflower or take a certain kind of fern leaves or branching in trees, so if, these exhibit similar patterns in smaller scale. So if you take a small portion of this leaf and magnify it, it is somewhat similar to the original. So this kind of things we see all around, but natural factors obviously are complex for young students to play with or think about with. So while we can introduce the simple constructions like the popular, the Sapinski triangle, like where you start with an equilateral triangle, you join the midpoints of the three sides and you break. So there are four smaller equilateral triangles and you remove the centerpiece. I think everybody here might be familiar with this. So stage wise, you keep repeating it. Now this is fun for students. And why is it fun? Because they see that something different is happening. And we number the stages from 0, 1, 2, 3, and so on. So, what are the interesting questions children can explore? Is that at any given stage, how many black triangles will there be? But interestingly, some students want to answer that what will happen, what is the white portion? The white portions are not there, they're holes, right? So, can we find a rule for the number of shaded triangles? So, even middle school students can engage with this problem, with this pattern. And what will be the shaded area? So, finding the number of triangles at any nth stage and the shaded area, colored area, or maybe the other part at any given stage. So, here this is a good context to bring about geometric sequences because as you can see, the number of black triangles is following powers of 3. So you have stage 0, it's one single triangle. At stage 2, there is 3, then it's 3 square and 3 cube. And because each of the triangles is further giving rise to 3 others. So there's a multiplying factor of 3. And what happens as n, you can ask these questions even in middle school, what happens as n increases, goes on increasing. And also observing self-similarity. So for example, uh, so you can ask children to build a table, note down how much will be the number of, how many will be the number of shaded triangles, and what is the shaded area. Now, when you look at area, you note that if the initial triangle, the stage 0 is 1 square unit, then what fraction is black in stage 1? Because you're 3 by 4, because you're breaking it into 4 parts and removing one part. But so they easily say 3 by 4, but when stage 1 to stage 2, they have to think a little. So what is the shaded area in stage 2? 9 by 16. So, but sometimes they say 9 by 13 and other things. But soon they realize that this black portion of stage 1 is itself divided into 4 equal parts and you removing one part. So again, it should be 3/4 of that. So each time there's a multiplying factor of 3 upon 4. So, and you can also introduce to little older students this recursive rules that the number of triangles at any nth stage is 3 times the number of triangles of the previous stage. It's an important notation to introduce at this stage. Uh, then you can ask them to pull up a spreadsheet. So, for example, let me see. Are you able to see? So there is a spreadsheet here. And so one of the things is that the pictorial thing you can't go up to very high stage. But if you want to really understand what's going on in the long run, it may be good to just write the stage numbers, use a simple formula. So suppose I just, so if you have access, you can just try this. It's very simple. Uh, you just have one column of numbers 0 to 20. Okay, should I show that? Okay. So since we start with stage 0, I don't know if you're able to see that. So if you start with stage 0 and you input a very simple equal to the previous cell plus 1. We can use the fill command, but here I'll simply drag the cell, and because I just need up to. You select the cell in which you've entered the formula equal to previous cell plus 1. So you get up to, let's say, up to stage 20. Now, we've already observed that the number of shaded triangles is 3 raised to the stage number, right? So we enter here 3 raised to, just click on the stage number because the stage number is fed into this column. So we just click on that. And similarly, shaded area, it will also lead to a geometric sequence of which are powers of 3 upon 4. And you again click on. So automatically when you drag, it will take the stage numbers from the column A. So now you can select both the column, both the cells where the formula has been entered and just double click because you have a column to the left. And if you want to see, they can just maybe select this and maybe if we insert a simple line graph or something. So you see that the number of shaded triangles is growing very fast. And if you look at the shaded area, the two opposite things are happening as the number of stages are growing. At least graphically, they can see something. So numerically, graphically, pictorially, symbolically, the 4 modes of representation, these together are important in exploring this practice or many other things for that. So, and any fractal that you can think of, it would be useful to come up with some kind of a spreadsheet exploration. So, of course, now the same Sierpinski. What stage is this of Sierpinski triangle? Stage 1 has, of course, nothing. Is stage 0 is the do nothing stage. It's just a single triangle. Stage 1 has 3. Stage 2 has 9. And this is stage 3. So can you see copies of stage 2? So if I look at the portion in the circle, it is stage 2. How many copies of stage 2 are there? 3. And so stage 3 has 3 copies of stage 2. Now if you enlarge stage 2, you look at stage 2, then it has 3 copies of stage 1. So at least this part children can do easily. And even at stage 3, you can identify copies of stage 1. So every stage has previous stages incorporated, and counting them leads us to the same geometric sequence. So, okay, so this is Mathematica's command, which has a Sierpinski mesh command, which helps too. So can you say which stage? It's fairly intricate now. Can you say which stage this might be? When children were asked, I'll tell you how they thought, how they answered. But children, I mean grade 9. Any guesses which stage this might be? We have to count those little triangles. But is there any other way to? Again, you see beautiful self-similarity because you see that this is 3 copies of the previous stage. And within that, you see 3 copies of that previous stage and so on. So how many times? Uh, number of shaded triangles? Which stage is it? We are asking. 8. Uh, okay, so yeah. So how did you guess 8? I don't know whether it's correct or not. I was just counting the. I said three of the little triangles and. Yeah. So when does the biggest hole come up? In which stage? Stage 1. So obviously this hole corresponds to stage 1. Then the next size hole corresponds to stage 2. Then there is the stage 3 on top. Then there is the stage 4 stage and up to 6. छोटा सा एक white ऊपर दिख रहा है. So 6th stage. So some children actually thought this way. So they were not looking, because they realized, I mean, when we asked them, why did you think this? They say impossible to count. How many little triangles will I count? But the white, the left out portion is giving me a hint as to uh, what would be the stage. So, but even to generate this on Mathematica, it takes little time. So, it's so after a certain stage, after 8 or 9, it will be difficult to look at the Sierpinski triangle. There are, of course, more the programming languages. Okay, now I would like to share this. I don't have many copies, but if you could take one and pass, maybe 2 people or 3 people could share one. You give half there, and then people will just pass. Yeah. Please take one. Don't take it together. I mean, I'll share it with you. I'll share the response. I'll share the PDF with you. I think you're all familiar with this. Written out. Written, okay. So what are these numbers inside these cells? 1, 1, 1, 1, 2, 1. What are they?
Identities, algebraic identities.
Yeah, what are they? Okay. 1, 2, 1, 1, 3, 3, 1. Next will be
1 4 4 6 6.
add, right? Right? Go on like this. 11, 11 raised to the power of. But after a while that fails, no? So these are what? The binomial coefficients, right? So this, okay. Now, so then as we can see, there are some, again, this has a lot of nice patterns. You have one, then the next diagonal is natural numbers, then you get triangular numbers and so on. There are all kinds of numbers. But now I just want to do a simple exercise. So you have this dotted, you have a much more condensed array, which has this little hexagonal cell. If you can just pass out, you don't have to do it right now, but you can see the grid. Now in this grid, uh, what we have to do, so you have these numbers, you have to shade the ones which are odd numbers. The cells which have odd numbers, you have to shade, and the ones which are even numbers, you leave blank. Is it okay? Anybody can do this. I want you to do this on this grid, where the numbers are not there. You have a grid of hexagonal cells. Like if you have this blank grid without the numbers, how will we know which ones are odd and which ones are even? Right? We want to only shade the odd cells. Okay, why do you want to do that? We want to do that because when we do it, yes, a pattern will come up. So obviously you might have guessed what pattern it will be. Relates to the suffix key. So now the problem for the students, I gave it to my first year students. I said, you color it. And they said, ma'am, we made a mistake. We spoiled the grade. Now can you give us more? I said, पहले से 10 photocopy करा के रख लो. And so now the odd numbered cells, first topmost cell is 1. Next row is 1, 1. Then is 1, 2, 1, right? So I'll only shade 1 and 1 and leave 2 blank. So it is blank here, correspondingly, if you can see. So how do we decide now, right? How will we decide which ones to color? So they had to come up with coloring rule, a coloring rule which would help them, which is different from looking at odd and even or knowing which are odd and even. Okay. But this also led to some interesting modifications of the Pascal triangle. Is that if you reduce it modulo 2, so for example, reducing this modulo 2 means that you replace the odd numbers with 1 and the even numbers with 0, or whatever, you divide the number by 2 and the remainder. So what will it become? 1, 1, then row 0, row 1, row 2. Row 2 becomes 1, 0, 1. Even number will become 0. Next is 1, 1, 1, 1. 1, 3, 3, 1. All are odd. Then is 1, 0, 0, 0, 1. Now you tell me, I don't have the fifth row. What should that be? So we are doing addition modulo 2. So we do 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. And you end. So we always start and end with 1. Next, 1. 1 plus 1 is 0. In modulo 2, 1 plus 1 is 0. 1 plus 0 is 1, then 0, then 1, then 0, and then 1. Right? So the ones have to be shaded, the zeros have to be blank in this coloring. So then we started seeing we can be, so if we have two shaded cells, so they translated this. If we have a cell here and we have a cell here, if there are two ones, then the cell in between in the next row has to be left blank. So if you have two ones, then the cell in between in the next row has to be left blank. So there's a coloring rule now, and that coloring rule was articulated as that if we have two shaded cells, two black cells, then the cell in the next row should be white. Similarly, if you have two white cells, I mean two unshaded cells, then the cell in the next row should also be white. So, but if you have one black and one white, then it should be next row should be black. So, if the parity of the color of the two cells is different, then the next row, the middle cell should be black, otherwise it should be. So, just reducing that to a rule, and then because sometimes what they do is they will shade all the ones on both on the ends of the grid. Then you lose track of what's happening. So we said, no, you have to do row wise. And when you do it, I like to share some of the. So this is actually this grid and the coloring patterns. Now, this is modulo 2. So there are only two colors. So you can use any color, of course. So they use this. But then they said, but what if we reduce Pascal? Now it was unleashed. So they said, what happens if we reduce the Pascal's triangle modulo 3? Or 4 or some other numbers. If you reduce modulo 3, that means you'll have 0, 1, and 2. Now you can use three colors. So here they've used, somebody has used green, blue, and white. So this is a variation of, this is also a variation of the Sierpinski triangle. Because what is happening here is, here the original triangle is, you see this? This has three copies of this. So there is a similar pattern there. And then it became a sort of a thing that they came up with many such coloring patterns. And so it was a very nice exercise to do. And it stemmed from this thing. And practice is something that you can keep doing. So, with every batch, you need not do the same thing. So even with a square, you try the same thing. It's called a Sierpinski carpet. So you divide the original square into 9 smaller squares and remove the center square. Now, the important thing is to ask children to create their own factors. So that leads to some very interesting this. Uh, so here, of course, you can ask similar questions. I'm going to breeze through this. This is a work of done by a student in her notebook. So she has used colored paper and she's actually cut out those holes using some sort of side with her permission. Then they challenge each other. Can you find out the area at the stage 3 and 4? What will be the green area and so on. Again, here you get a geometric sequence because if 1 is the area at stage 0, then it becomes 8 upon 9 and it becomes powers of 8 upon 9. Uh, this, of course, was done by a student this year, but in the past also there have been many. In fact, there is this basketball court in Spain, which is actually a Sapinski triangle created, sorry, Sapinski carpet created, which very many children have made smaller parts. I think you can see here. And so it's fractals are popularly used for aesthetic purposes also. So I'll not get into more, but see, the thing about fractals is idea of recursion and iteration can be brought in. Now, if you look at the Koch curve, you can see that by stage 0, 1, 2, 3, 4, it becomes really fairly intricate. With older students, you can do a lot more. So, for example, you can ask them. So, if you do this onto the sides of an equilateral triangle, then you get the snowflake. So, interesting questions to ask is, of course, what is the number of line segments at any state? Again, you will come up with a geometric sequence. And what is the what is the perimeter? Overall length of the entire thing. That's also a very nice exercise. But what is more fascinating is what happens in the long run. As the number of stages grows, what happens to the area? Now, see, if you look at the equilateral triangle area, we all know the area is root 3 upon 4 into side square. The side is suppose 1. So initial area is root 3 upon 4. So has the area increased or decreased or what has happened? Next stage. It has increased because you've added 3 more small equilateral triangles to it. Then from that stage to this, you further added in this 12 more triangles. So you're going on increasing the number of triangles. So what should happen? So the area go on increasing and what will it approach? So you can actually give them this exercise. And now, so this is again a student's work. So what happens is that what is your feeling as n tends to infinity, as the number of stages grows, what will happen to the area enclosed inside this? So let's have a look at a spreadsheet. So let's look at the spreadsheet where this has been done. Uh, so this is the entire data up to stage 20. So how many line segments? So this obviously grows fast. 3, 12, 48 is 3 into 4 raised to the power n. Length of one line segment at each stage is decreasing. Perimeter. Now what happens to area? If I just select this and the total area enclosed and I insert a graph, I get to see that after a while the area steadies out and we can see it numerically. This was, it really took the students by surprise. ये कैसे हुआ? तो बढ़ रहा है, triangles तो बढ़ते जा रहे हैं. Triangles तो हर स्टेज में बढ़ते जा रहे हैं. But one child gets up and says, लेकिन, sorry, हाँ, but number of triangles is increasing, but the they're getting smaller and smaller. So somewhere they seem to compensate or what. So actually we see that it approaches 0.69 something, and that actually works out to 2 root 3 upon 5. But they wanted to know how to show it. So basically they actually used the infinite geometric series formula. And it was very easy to show that if you write out the series of the sums of uh, if you write out the series of the sums, you will see that it actually approaches 2. And using school mathematics, in this can be done. This has largely been done with grade 11, where they get introduced to geometric sequences. So there's a lot of possibility in fractals. And with older students, we can even talk about matrix transformations. So what happens if you take the Koch curve में क्या होता है? You take a line segment, you divide it into 3 equal parts. In the middle part, you remove the middle portion like here, and you raise an equilateral triangle like this, right? Now, which matrix transformations will convert that unit length? Let's say this starts with 0, 0 and 1, 0 to this shape. So we need four such transformations. One is shrinking this line to one third its size. For this part is shrinking the line and shifting it. So shrinking and shifting is F4. Here it is shrinking and rotate, shifting and rotating. So a sequence of matrices. So this was given to grade 12 after they studied matrices, and they had to figure out which were the matrices which when multiplied would lead to. And of course this four set of these things are called iterated function systems. This set of four applied on the entire Koch curve at stage 0 lead to stage 1. From stage 1 you will get to stage 2 and it goes on like that, right? Uh, in our book we have also talked about space filling trees. Now this is again I was saying that we should encourage, I would like to engage you to engage in this counting problem. Okay. So let's say like the Sierpinski, but it's not a Sierpinski triangle. I just have a grid, triangular grid with four smaller triangles, right? Suppose I take the center of the middle triangle and I draw these three lines which are exactly of half unit. Okay. So not half unit, it is so basically this is one third of this side. We can prove that. So I have three lines, right? There are three lines coming out, and what angle are they making with each other? 120 degrees, right? Okay. And I remove the grid from the back. So the last stage is the what we call the first stage of a tree, a certain kind of tree which is called. Okay. Now what do we do? So this is called T1. How many branches are there in T1? Three branches. Okay. Now what I'll do is this is stage 2. So what has happened in stage 2? So what we have done is I have three lines, and from these endpoints, I have raised three of half the length of this, right? So we repeat it here and repeat it here. And in the middle part, I so what will happen is that if you imagine that this grid is further divided into smaller triangles, you will get 16 triangles, small triangles. And you keep repeating the process of connecting the centers. Now you note that this is the center is connected to the center of the upper equilateral triangle. This connects the center of this to the triangle on the left, and this connects to the triangle on the right. And this process is repeated. Keep on repeating this process. How many branches do you have been added at this stage? So we have added to the three endpoints. These are called edges of degree 1. Oh, sorry, vertices of degree 1, because from this endpoint there's only one edge coming out. From this there's only one. From this there's only one, right? So we add 3. So I've added 3 into 3, that is 9. But I've also added 3 here. So 12 branches have got added, right? But it gets more complex.
Sorry to disturb you, ma'am, but we are running short on time.
Ah, okay. So this at T3 again it gets more complex, but and this is what it looks like, intricate and beautiful. But the exercise which should be given to students is, can you find a formula for the number of branches that are getting added at every stage and the total number of branches at any given stage? So that's, and this helps to, this picture will help because the red ones are the ones which are getting added. So if you have 3 initially, you can see the 12 which has got added in this stage. And this is a fractal again. So these are called space. Ultimately, what is happening, the entire space inside the triangle is getting covered. Correct. Yeah. Yeah. So this is what we need to encourage students to do. Use colors, give them opportunity to So I would urge you to, and of course you can have 3D versions also. So a lot of students have fun making practice greeting cards. So these are some of the cards. This resembles a 3D version of the Sapinski triangle. And it's a simple exercise of folding paper and cutting, folding and pushing out cells, giving a 3D effect. And so originally this was discussed and this card was again it has very interesting powers of the biggest cell is one, the next size cell is two, the next size cell is four, then it is 8, 16, and so on. But then one student said, I'll try a variation of this. He made this one which has a double this thing. So a lot of interesting things can be done. So time is out, so I'm just going to conclude now. There was a lot to be. So, so now, just before we leave, I will just ask you about one problem.
मैम इसमें हिस्ट्री का हमारे पास 6 बजे तक का टाइम है अगर आप चाहें
हो गया.
अगर मैम आप
I
चाहें
just discussed this and leave it. So, I think many people are familiar with the birthday paradox. So basically, in this room, how many are there people who have the same birthday? Yeah, that's so. Do you think there are two people in this room who have the same birthday? Birthday means obviously the date, so you don't have to disclose your age. So, क्या लगता है? So, question is that how many of us are in this room? Rather, how many people should we gather in this room to be sure that there will be at least two people who have the same birthday? Time, I don't have time, otherwise I always write down the months and I ask people to just quickly tell their date. 32 people. Okay. To be sure that they'll have a match. Okay. But normally, what is the normal, what do you think people say when this question is asked? 360, actually 366. They say that if you gather 366 people and 360, there are 365 people with different days as birthdays of the year. And the 366 person obviously will have a match with one of the 365. Okay?
मैम फरवरी 29
So 367 in that case. Actually, this is the initial reaction. And but interestingly, that in much smaller group sizes, in group size of 50, 55, even 60. I mean, 60, you are sure that you will find two people. We don't need so many of us, and I'm more than sure that there are people in this room who have obviously shared a birthday. So, how do we convince people? आप convinced होते अगर मैं सबको पूछती वो सबको पूछने की जरूरत नहीं होती मैं I would have started from one end. If she calls out her birthday, okay, what's your birthday? 30 October. Her birthday is on 30th of October. 13th or 30th? No, she's 30th. No, so as they would call out their birthdays, anyone else having that birthday will just raise their hand, so we will know there is a match, right? So if we do it, it's pakka. Okay. So, but I don't have time, so I won't do it. But I'll quickly show you that what can you do in the class? Hanji, क्या? आज है अच्छा. Many happy. Okay. Right. So, what would you do with children in the class? So what you could do is you could ask each child, suppose you have a class of 40, ask each child to contribute, say, two birthdays. You don't even need 80 actually. But ask them to contribute two birthdays. One is their own and one is some family member of theirs or somebody they know. And you put the chits in a box and you just shuffle it up and randomly pick up. And you will see that a match will come up. So the people whose dates they're writing, you have to imagine that they are in Europe, right? So, but If you have to really try it, you can easily quickly simulate it. So I'll just show it before ending the session. So it's already created. So what we do is uh, we just create a simulation where we have numbers 1 to, let's say, 60, right? The first column is numbers 1 to 60. Then the next column, we simulate the month. Now, months can be represented by what? 1 to 12, ranging from January to December. But how do you do this? So we do it like this. So I just need to put 1. I just need 60 because I'm claiming that in 60 dates you will find a match. And now randomly I want to generate numbers from 1 to 12 for the month. And within the month I need a date, right? So I'll just say use a command which is called ran between. So ran between 1 comma 12 will create a random number between 1 and 12. And you just you click on the column. So we get months. Can you see the months? Yeah, rand between. RAND between 1 comma n. If you want a random number between 1 and something, you just type. So I want it between 1 and 12. Now I drag the same thing and I edit it. I need, of course, every time you click the sheet, a new set of random numbers will get generated. This is not a good way to simulate this problem for obvious reasons. But let's say now I made it 1 to 31. So what is the first birthday? 30th of July, right? 30. So, so I double click here. So I might get some impossible dates, so we'll ignore that set. Now, how do I check if there are 60 birthdays? इसमें match है कि नहीं? So I have 11th of March, 23rd of December, 29th of March, जो भी है. How do I check if there's a match? It's difficult to check. So what I do is I do a simple arithmetic operation. I multiply the month by 100 and add the date. So basically, I convert this 3 and 11 to a 3-digit number by doing this month into 100 plus. And why do we do this? Single number, and that can be sorted. So there is a match, they would come together. So if I double click on this, I get the birthdays. Now, what is 906 indicate? 6th of September, 11th of February, like that. So now, how do I check if there's a match? So all I'll do is I'll right click on this, copy it into another column, paste the values so that I don't lose. I get a new data when I click on this column, but the earlier data is here. And then I select this and I just sort. Yes. So do we have a match? Everybody will kill me if there's no match. There's a 15 also. 15th of March. 412. Then more. I mean, at least one बोला था ना, तो आगे देखने की जरूरत नहीं है, right? So we stop here. But this is not. Don't do the simulation before you make them. Ask them to go to different classes. Then we have group sizes of at least 50 in every class in many schools, right? Definitely there's a match. So then they say, oh, tu hoga, ma'am, you too. I want to see a group where there are people coming from all over the place, as if they tend to think that if you are in the same class, then you are obvious that there would be a match. But then when we collect, they have to collect dates from different people and collect them together and then find the match. That will be much more convincing. After doing that, and of course, with older students, one has to discuss why it happens. Then you have to, of course, get into probability, and that always works. So, with this, I stop and thank you for such a